Assalamu alaikum wa rahmatullahi wa barakatuh. Once again, last class we have learned how to draw the bending moment for two-way slabs. We learned how to find the coefficients, and we compared whatever we have done with Excel. Okay. Today as well we are going to try another software. Okay. Today we are going to try another software as well, which is called Tekla Test. Okay. Now, if we go, or let us keep the Tekla later. Or Tekla. No. Okay. So we'll go with Tekla first. Now, can you see? You can see, right?
Yes, Mr. We can.
So this is Tekla. Okay. This is whatever we call Tekla TEDs. There are three major software for Tekla. There is Tekla TEDs, where it carries the manual calculation. There is Tekla structures, which is for detailing, and there is another one which is Tekla structural design for designing. Okay, so if we go for new, you can see that there are different things here. We have beams, columns, concrete, floor, euro codes, different things are there. Okay. So for example, if I go for floors, I have different things under floors. We have stair design to BS code. We have stair design to EN, that's euro code. We have slab design to BS code, slab design for euro codes, raft foundation, flat slab design, and other things. So if we go for RC slab design, and then we go for calculate, first it will tell us, are we talking about one-way slab or a two-way slab? We have learned for a one-way slab, it might be either simply supported or continuous. And we have learned as well for two-way, there is simply supported and there is restrained, if you remember. Okay. So if we try to solve the same example that we were trying, which is this one, we want to compare the coefficients and the bending moment. We'll go to, okay. 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 Now you can see both. Turn off your mic. Turn off your mic. Okay. Now, if you see, this is a two-way slab. Okay, this is a two-way slab. Here we are going to check. It's a two-way restraint. Do you want it bars or mesh? Okay, meshes are small bars, normally used for ground slab. So we are going for bars. Shear, yes. Bunching shear is not required. We are going to learn later why bunching shear is not required for the meantime. Spine by deflection ratio, reinforcement cover check, appropriate sketch. I want all of them. Overall depth of the slab. So if we go and see here, H or the overall depth of the slab is 180. So we are going to go for 180. Cover is here 35. Here it's 20 according to the question. So 20, and then we have 20. Diameter. Diameter here is not given, but we can assume that the diameter is 10 pi. Grade of concrete or grade of steel here, 460. Grade of shear reinforcement for the links, 460 if there are any links. Grade of concrete, 35. Diameter for the top bars and 10. And then the partial factor of safety for the material of steel is 1.05. 1.05. So 1.05. Next. It will ask what is the length of the shorter side in millimeter. So Alex is 6,000 or 6 meter. So 6,000. Ly is 9 meter or 9,000. Design ultimate load per unit area. What is your N value? So we have N value of 11.8 here. The total loading for W, so 11.8. Okay. And then we have continuous beta redistribution factor. Remind me later to explain for you what's the meaning of redistribution of moments. Minimum is 0.13%. Ultimate shear force, still till now we didn't get it. you can keep it as any value for the meantime. Okay. As well. Although 100 is too much. Let's keep it to be 20. Okay, so it will tell you how much is the area of tension steel. And then you need to pick appropriate. You need to pick appropriate reinforcement. So you can see 6 diameter, 8 diameter, 10 diameter, and then we have spacing 75, 100, 125. No, it will affect, of course. It will affect the small. This is only because I didn't have the shear force values from the other software. Okay, or Excel. So you can do it in Excel and then return back to do it in Excel. Or use your table in the VS Code to find your shear force. So basic span by effective depth ratio, this is going to be 26, and we'll learn why it's 26. Cover is permissible nominal cover is 35, that's fine. Next. Now you can see, according to whatever I have input, it was calculated. I have overall depth, I have dx. Now if you can see here, we have diameter is 10, dx, if you remember, dx is d capital minus cover minus diameter over 2. Okay. And then the cover is 20, dx, dy. And then here explanation showing what's the meaning of dx and dy. We'll come to this one, dx and dy and everything. We'll come to it later. Now, for the meantime, we want only to check the coefficients, whether we have got the coefficients correctly or not. So you can see the coefficients for me are 0.4, 0.024. So if we go and see here, we have 0.04 and we have 0.024. And then we have 0.053 and then 0.053. And then we have another one which is 0.032. So you can see 0.053 and then 0.032. Now, of course, the good thing here that you got your whole calculation according to whatever you have studied in the college. So K, if you remember, is equal to M divided by FCU VD square. K dash is 0.156. Z, it's either B multiplied by 0.5 plus under root of minus 0.25 or 0.25 minus K divided by 0.9 or 0.95, whichever is lesser. We have studied everything here in the design. The only thing that this software is going to show you the calculation instead of writing it. So minimum reinforcement, maximum reinforcement, checking for the cracking, checking for the cover. So everything has been done already. So all the calculation or the design has been done. Okay. Now what you need to do, we are going to go for from here, send it to, and then you can send it to Tekla for Word. So now if we go and open our Word file, you can see that this is coming to you directly in the form of a Word file. Okay, so this is Tekla, which is going to do for you a manual calculation. Okay, a manual calculation, something similar to Excel, but it will show you even.
Mr. Again, please.
Again, for what exactly? Which point?
For Tekla, when you share it.
Using the software or finding the coefficient? For using the software, we'll come to it later. Now, for me, only I need to explain for you that the coefficients, you can find them using different methods. I don't want to spend a lot of time now explaining Tekla. I need to go for first explaining the full procedure in manual design, and then we can fully compare it. Are we okay?
Yes, yes.
Now you have finished only the coefficient. My main intention in the Excel or in Tekla that we are going to compare the coefficients on. Right? You still didn't finish the other things. So before you need to finish them, understand them manually, and then we'll come to the software to compare. Are we clear? Okay, very good. Very good. Okay. Now returning back to our class. So I say for you. Are we fine now? Can you hear me now?
Yes, yes. Yes, Mister.
Okay, now last class, if you remember last class, in the last class I have told you to try example 1, 2, 3, 4, if you remember. Have you done them? Any issues that you have faced? I told you, if you remember, I told you that you need to do 1, 2, 3, Or
Excuse me, sir.
yes,
Can you hear my voice clear?
yes. Somehow.
What about now?
Okay.
My issue is about number 4. Question number 4. What should we do?
You need to find the coefficient. My question is clear. I have given you already something similar. This problem that I have given you in the exercises that you need to do. Previously, I have told for you one document that I told you should try. You remember?
Is it only which is related to the coefficient?
Yes, you need to draw the bending moment, find the coefficients, and then draw the distribution of these. The distribution of loads to the beams.
Okay. What about part B, C in question number 3?
Yeah, distribution of loads. I have explained for you.
Yes.
I have explained for you already the lead lines. Do you remember? Lead lines, two areas, 3 areas, 4 areas, 5 areas. Do you remember?
Yeah.
So that's loads distribution to beams.
Yes.
So any other issues on these particular three? Now this one.
Only
Exercise.
uploads by drawing.
Yeah, only drawing. Only show the distribution, not the values. Because you don't have the values of loading. You cannot get the value of loading.
Okay. Thank you, sir.
Okay. Do you want me to give you a hint? Or it's fine? It's not appear for me. Others are not seeing the screen. Others, are you able to see the screen?
Yes.
Now, Suleiman? Okay. Okay. No problem. Okay. So I'll leave it for you then. 1, 2, 3, 4. And as I told you, 1, 2, 3, 4 were from the previous exams. Okay. Since we are asked to draw the bending moments, find the coefficients, draw the distribution of beam for number 4. This I think was a 3 marks question in quiz number 1. This as well was a question in the final exam. This is a question in quiz, I believe. This one as well, I think, in a quiz. Okay. So I think you should try them. You should try them and then we'll go and give it a go. Or do you want me to give you hints about them? I think you should try better.
Sir, if possible, give us the hints on the last because I
Give us. I cannot hear your
didn't
voice.
understand. The question, exercise number 4.
Yeah. What about it?
The first drawing in left side. What is the meaning of that 2 squares?
It means that there are 2 slabs, and I want you to draw for this slab. Are we okay? Do you want me to explain it or are we okay? Yes. No. Yes. Yes, for what exactly? Okay, I'll explain only one of them, which is number 4. You can try the other ones. Okay, you can try the other ones. Now, the first thing they were asking us that we need to draw the bending moment diagram, and then we need to get the coefficient, and then we need to draw the distribution. Okay. So if we take case number 1, let's say that this is case number 1, case number 2, and then case number 3. I'll take the first one. Well, let us start with the easiest one, which is case number 3. Now, case number 3, is it a one-way slab or a two-way slab? There is no answer key.
One-way slab.
You need to try them. If you answer them, you can approach me, or if the students are having a lot of questions about them, I can upload at that time the answers. So this is a one-way slab. So the bending moment will be drawn for the short or the long. One-way slab, the bending moment will be drawn short or long. Short. So this is my span. This span is supported only by one beam here. So this is now acting as a cantilever. The coefficient for a cantilever is 0.5. Because in a cantilever we have the bending moment, which is del U square over 2. So 1 over 2 is your coefficient. Did I explain for you the cantilever and the coefficient is 0.5? Yes, I did. Okay. Did I explain these things? I say that the coefficient is 0.5 or half. I did, right? Very good. Case number 2, beams are all over. So there is a beam here, there is a beam here, there is a beam here, there is a beam here. This is 5 meter, only one dimension has been given. Means that the other dimension is 5 meter as well. So this is a two-way slab. Your bending moment is going to be of this way. Where you can use the code now. you can get, or you can use the code to find the values of mx and the values of m1. Here it does not matter what's your mx and what's your m1. And your ly over lx is going to be 1. Now for this problem, the whole tricky point is available in example number 1. Now in example number 1, we have this slab where it's discontinuous from here. It's discontinuous here. It's discontinuous here. And then it's discontinuous half of this element. Now the code says for us that we have either discontinuous or continuous. We don't have half continuous and half non-continuous. But our logic says that this slab can be divided. If I divide this slab into 2 zones, This is zone number 1, this is zone number 2. I'll be easily drawing the bending moment diagram. Okay, so two cases will be there now, case number 1 and case number 2, where for case number 1, your bending moment diagram is going to be like this. And for case number 2, where your bending moment is going to be for this way. And then for the other direction, it is of this way. Are we okay? So when I ask you to find the coefficient, okay, here there is 0 and there is a value. So of course you will be designing for the maximum, which is this one. Here between this bending moment value and this bending moment value, you need to pick one which is the biggest of the two, which is of course going to be case number 1. Are we clear? The question is very easy if you use your logic. Okay, very good. So we'll go directly then. We'll go directly to the other things. Okay. Now, why I'm concentrating a lot on drawing the bending moment diagram, because bending moment diagram is related to your reinforcement. If you know where you are going to keep the bending moment profile, you should know where you are going to keep the reinforcement. Okay. So if we see here, this is a simply supported. Simply supported are going to have cracks from the bottom. Or how would you know? You will see the bending moment. You are going to see the bending moment diagram. Now, for a simply supported, we say, for a simply supported, the bending moment is going to be of this shape. Now, if the bending moment goes down, it means the crack will happen at the bottom. If the bending moment goes up, it means the crack is going up. No, of course, it is still functioning. You are not going to cut the slab in reality. You are using your logic to finding out the strip of bending moment for that particular slab. It will not be divided. In reality, there is no two slabs. Okay. So did you get the cracking point? We said if it goes down, then the crack is down. If the crack is down, then the reinforcement will be kept at the bottom. So if you know how to do your bending moment, then you should know where it will crack. If you know where it will crack, you will know where to put your reinforcement. Are we fine? Very good. Okay. Going for, okay, this is what we have explained, which is a bending moment. Now going for another scenario. Now for this scenario, you will see that you have positive bending moment going down and then a negative bending moment going up. It means this will crack at the bottom and this will crack at the top. So if we go and see the cracking, you will see this will crack at the bottom, this will crack at the top. Are we clear?
Yes, Mister.
So if you know where it cracks, you should know that the reinforcement is going to be like this for the bottom, and then there is another reinforcement which is going to go at the top to avoid this cracking from happening. Are we fine? Very good. So everything depends on the bending moment. If you know how to draw, you shouldn't have any issue. About this case, once again, it will crack up, up, bottom. So when we go and draw, up, bottom, up. Although in reality, we are going to extend the bottom from the beginning till the end. Although in reality, we are going to extend the bottom from the beginning of the element to the end of the element, even if there is a small point where it shows you that there is a top only. And the main reason that instead of it's a very small area. It's a very small area. So instead of cutting the reinforcement, bringing laborers to do a lot of work of cutting the reinforcement, it's cheaper for me to keep that small pieces with the reinforcement. Okay.
Mr. Repeat that point once again, please.
Okay. Now, if you have, let us say that you have a slab. Now, the length of the slab, let's say the clear length of the slab is 6 meters. And your support, okay, your support is 200 millimeter or 0.2. Okay, and let's assume that this was continuous as well. This was continuous as well. Now, what will happen in this scenario? You will see that your bottom reinforcement will go from here till here, and then we are going to have a top reinforcement here. Now, once again, the bottom reinforcement will start after the support, right? The distance between the first bottom and the second bottom is very small. So for me, instead of cutting this small bars and then replacing it once again, it's easier, cheaper, more effective for me to keep it all the way. Are we clear? The span normally, if you see your span is having more length than your support. So this is span number 2, for example. This is span number 1. This is span number 1, or span number 3. So you can see the distance will be here. The distance between the span and the span are very small. So it's better to connect them. Are we okay? That's in reality. Okay, that's in reality. For a slab bends in how many directions? Slab, it bends in how many directions? 2 direction or 1 direction normally. We said, if you remember, if it's one-way slab, it has one major bending and one minor bending. If it's a two-way slab, it has 2 major bendings. Do you remember? Okay. Once again, if it's one way, there is one major and there is one minor. In case of a two-way slab, there are 2 majors. Okay. So eventually, whether you are talking about a two-way slab or a one-way slab, there are 2 moments. But in fact, one is major and minor in case of one way, or both of them are 2 major in case of a two. Since there are 2 moments, even if one is minimum or minor, that moment is going to cause you to have reinforcement, whether it's calculated or whether it's taken as the minimum reinforcement. So you can see that due to the 2 moments, we are having 2 reinforcement sides, because we are having a moment in this direction and then we are having a moment in the other direction. Are we clear? So one reinforcement side, one of the sides of the reinforcement is going to resist the first bending, and the other one is going to resist the second side. Are we clear? It's like a nut, نفس الشبكة. Okay. They will take the bending from both sides. Now that's for a column. For a beam, already we have discussed. For a beam, it's only one moment. So that's why you see only one direction reinforcement. For slabs, there will always be two direction, even if it's one way, because there is one major and there is one minor. Okay, for beams, we said one direction only. So if it's one direction, we cannot see that we have reinforcement here. We don't have any of that reinforcement because it only bends in one direction. It's very small to bend in the other direction. Are we okay? A very good example of a beam is a ruler. You can bend it in one direction, you cannot bend it in the other direction. Major moment is the moment which require you to have a specific reinforcement. Minor moment, normally, it has a very small value, and in that scenario, the minimum reinforcement governed by the code is going to be sufficient. Major is having a big value, minor is very small. It means that if you use the minimum given by the code, it will always protect you in case of the minor. That's why in one-way slab, we only calculate one moment and the other side is taken as a minimum. In two-way slab, both of them are major. Both of them are having high value moments. So in that scenario, you need to calculate for both sides the reinforcement. Are we okay? Suleiman? Okay. Now what about column? Column, is it an axial member or is it a flexural member? Do you remember axial and flexural? Do you remember when we talked about axial and flexural? Column is an axial member, right? Column is going to be affected by compression. Flexural are going to be affected by bending. Okay. Now it means that the load is going to come vertical to this particular column. Okay, the load is going to be vertical to this particular column. Now you will see if you try to bring anything and you try to compress it, you will see that this will try to go down. Remember, it's going to try to go down, right? If you try to compress it. Now, if I want to go and protect it from going down or from crashing, it's like a can. Do you know a can of what you call soft drink? It's a can of soft drink, and you try to push it, you can see that it will go down if you press heavily. It's 7 up, please. Okay. So what happens in this scenario? Are we going to put the reinforcement in this side? Or are we going to put the reinforcement in this side? Is it side A or side B? If I want to stop the column from going down. Now the correct answer is going to be B, of course. Okay, the correct answer is going to be B. If I don't want my column to go down, I put the reinforcement to be vertical, not horizontal. That's why we see our reinforcement for the column in this way. Are we okay? Are we okay? Okay. So now we should be starting. We should be starting the actual lecture of designing a solid slab. We have learned the basics. You can say that now we are going to enter the actual thing in terms of designing. Okay, we have discussed the different things when it comes to the bending moment for the different elements. We have learned how to do the relation of bending moment and reinforcement. We have learned a lot of things in the basics. Today we are going to go for the design, the full design of a solid slab. But before going for the solid slab, we should understand the different types of slabs first. So what are the types of slabs that you know? What are the types of slabs you know? There are different types of slabs, right? So we have solid, flat slab, flat slab, flat slab. Conventional is solid. Conventional is solid. Solid. Okay. Waffle. Waffles. Okay. Now, when you talk about doom, still it returns to be one of the categories. Okay? It returns to be one of the categories as well, but not a separate one. So it follows one of the categories. It depends on whether it's supported or not. If it's supported, then still it functions as a solid slab, although that it's circular or curved in shape. Anyhow, whatever we are having here, we are having different types of slabs. One is solid slab, and you see in this solid slab, the slabs are supported. The slabs are supported by beams. Okay, the slabs are supported by beams. So whatever Sulaiman has said as conventional, we call it conventional or traditional or solid slab. Okay, where our slab is supported by beams, and normally it's recommended. Normally it's recommended that the slab is going to be from 5 to 6 meters. Now, of course, I can go for 10 meter. I can go for 10 meter, but in that scenario, the depth is going to be very huge. Okay, if I increase my span, and when we refer to 5 to 6 meter, always we are referring to the short span. Okay. So when we talk about the short, which is 5 to 6 meter, 5 to 6 meter, if you go beyond the 5 to 6 meter, it means the thickness of the slab is going to be more. And in that scenario, there are other methods or there are other types of slabs which are going to be more efficient or more, let's say, economical than solid slab. So the typical range of 5 to 6 meter does not mean that you cannot go more than 6 meter, but it means that the economical range should not exceed 6 meter for a solid slab. The other type is a hollow core. The other type is a hollow core. Now, what is the main difference between that slab and this slab? Solid slab and then the hollow core. Now, in the hollow core, 5 to 6 meter, Suleiman is a short span. Short span. Always you are designing for the short. Whatever dimension we talk about is going to be short only. So when we talk about slabs, we don't refer to length and width anymore. We refer to short and long. Okay. If your long span, if your long span is more than 6 meter, you shouldn't have any issue. The only thing, I mean, your long span. I mean, if your short span within the limit, then it's fine. Okay. But of course, you cannot go very what you call very long in terms of the other dimension as well, because it will fail in other criteria. It will fail in deflection in that scenario. There is no limit. There is no limit for a long span. There is no limit, but the only thing that you need to make sure, because we are referring to loading. Under loading, there will be bending, there will be shear, there will be deflection. If you keep a very long span, even if the short span is limited to 6 meters, you might be having a problem with deflection. Okay, that can be solved by putting intermediate beams all over. And if you put intermediate beams, once again, the slabs are going to be cut into smaller pieces. Now, hollow core is used normally. Hollow core is used for precast, as Ittihad said, or pre-stressed element. I think most of you are studying pre-stressed now, or you have studied, or you are going to study next semester. So hollow core is used a lot with pre-stressing forces. Why we are using it? We are trying to remove. You can see that areas are removed. Okay, areas are removed from inside, just to make the just to make the slab to be lighter a little bit. Because if we are having the slab to be lighter, it means that you can extend the distance between one column to another column. Are we clear? Another method is rubbed slab. Okay, rubbed slab, something similar to our solid slab, but rather than having only supporting beams, you will be having inner beams all along the slab in one direction, and these are called to be your rubs. Okay, so something similar to solid slab, but rather than that, we are having intermediate beams all over. Okay, and this is very good when it comes to little bit longer span. Okay, longer span. You can have it from 8 to 12, or 12 to 13 as well. Okay, for a rubbed slab. Other than the rubbed slab, we have a flat slab. Okay, we have a flat slab. And you can see here we have showed some differences between the solid slab and then the flat slab. You can see one main difference is shuttering or formwork. Now the shuttering here is easier for the flat because it's a flat slab. We don't have inner beams. These are the position of beams. Okay, and you can see wherever there is a beam, okay, wherever there is a beam, there is a wall. Okay, wherever there is a beam, there is a wall. Okay, here. So the loads of the walls will be taken by the beams. So you don't have major deflections. We don't have a major deflections because of the walls. In case of flat slab, you will see that there are no beams normally supporting your walls, which are very heavy. Okay. So that's why normally the flat slab is going to be a little bit thicker. Okay, a little bit thicker than a solid slab. Okay, it's normally starting from 250 and above, the thickness of the slab. Okay. And normally it is good if you go for a flat slab starting from 6, let's say, to 10. And when we refer to 6 to 10 meter, we are referring to the distance between the columns. 5 to 6 is the distance between the columns. The last one is a composite. Do you remember the example of a simply supported slab, two-way slab? Do you remember? Do you remember when we said a slab laying on the top of A beam, a steel beam. Do you remember? Now you can see here that this is a slab and this is your steel beam, but they are connected. They are connected between each other, right? They are connected. So they act as restraining. They don't act as separate elements, they act as connected elements. Okay. Now of course we don't have steel slabs. If I'm doing a steel construction, steel column, steel beam, we don't have steel slabs. What do we have? We have something called composite or composite. Okay, where you are having a steel sheet. This is the sheet. What do we call this sheet? This sheet, and then at the top of the sheet we are having a water slab. What do we call this sheet? We call it as GI or galvanized iron sheet. Galvanized iron sheet. معروف بالعماني بالتشينكو, if you know the chinko. Okay, so we have galvanized iron sheet. At the top of the galvanized iron, we are having the slab, the concrete slab. Are we okay? So there are different slabs, or there are different types of slabs for the different functions. So you should know, you should be able to know based on this thing or based on this particular structure, I should be using this particular what you call this particular type of slab. This is a restraint now. They are connected with each other. It's not fully fixed. It's not simply supported as well. You cannot say any joint. You cannot say any joint in a building is normally fully fixed. Okay. So there are certain things normally we follow. Certain things normally we follow. It says for you that you need to select certain things before. You need to check the grade of concrete, grade of steel, sizes of elements. You need to estimate the dead load, life load. After that, you need to calculate the moment. So general procedure, the general procedure of designing a solid slab. Now, if we talk about designing, okay, what is the most important thing that you need to consider while designing a slab? If I want to design, for example, a chair, what are the things to be considered while designing a chair? If I want to design anything in life, what are the things to be considered? Load other than load? Other than the load? Shape, area, chair bed, capacity, material. Okay. Usage, soil test. Okay. Bending. Okay, now it's sufficient. Money. Okay, we started to a little bit go away, but anyhow. Okay, to keep it simple, for me to design anything in life, before designing it, I should know how it fails, or how is it possible to be failing. If I was able to remove that failure from happening, or to avoid that failure from happening, then it means that I have successfully designed my element. Okay. So once again, if anybody asks you how would you design any particular element, the first thing you should know how this element can fail. And if you solve the problem of failing, it means that this element has been designed. Are we okay? Now, when we talk about a slab, how do you think that it's possible to fail? How is it possible to fail? Under what exactly? What are the possible failures of the slab? Okay, can I just hold them for you? Can I say that it might fail in bending? It might fail in bending. There is no load capacity in slabs. As we said, slab is a flexural member which will be affected mainly by bending, not by loading. Okay. Uh, it's not overloading. We are checking bending, not overloading. Okay. So bending, cracks, as Zahra said, shear, as Sarah said. Do we need to check for deflection? Deflection of cracks, as Zahra said. Deflection, do we need to check? Do we need to check that this element is durable? So certain criteria I need to check. Certain failures are happening. Okay. If I avoided or if I check these failures and they are not happening, I can say that this element has been designed correctly. So I have kept a roadmap in which we are going to check certain things. So the first thing, we need to check whether it's a one-way or two-way slabs. Is it important to check? Is it important to check whether it's a one-way slab or a two-way slab?
Yes, yes.
It is important. It's important because we have different tables for the different scenarios. Right? One-way slab is going to fail in one direction, or it's going to have major bending in one direction, while two ways are in two directions. Do I need to check whether the support is going to be restrained simple, or it's not important? Will the value change if it's simple and restrained? Remember, if you remember for a restraint, we have talked that this was a simple case, right? This was a simple case. This was a simple support. Do you remember this case? So for a case of simple support, we are using this table. There is only one small table which has no cases because it's a simple support. For the restraint, do you remember that we have taken 9 cases? Is it important for me to know which table to use, whether the small table or the large table? Is it important for me to know which table to be used? Okay. Is it important for me to choose the correct properties of materials? Is it correct to choose the proper grade of concrete, proper grade of steel? Do I need to check for durability conditions? Do I need to check whether there is a durability? I mean, this element is durable or not? So all of these things are going to be mainly are going to be the process or the steps that you are going to do. Okay. Now, anyhow, there are five failures. There are 5 failures you need to take into account when designing for a slab. One is durability. Second is bending. Third is area of reinforcement, that you should not exceed the minimum and the maximum. Fourth is shear reinforcement. Fifth is deflection. If I was safe in these 5 areas, I can say that my element is properly designed. Now let us start the first one. Now this is my problem. We have a dimension of 5. We have a dimension of 4. Okay, 5 and 4. And then it says for us that it's 175. It consists of a strained slab support monolithically. Monolithically means that the slabs and beams are bored with the concrete together. No, that's it. So I mean, it depends. It depends on the type of elements that you are using. Normally, we don't recommend to go for a simple supported slab unless it's really mandatory. Normally, if you see your vertical element, there is a vertical element which is a column or the wall which is supporting your slab. Okay, which is supporting your beam or your slab. And then there is the weight of the element which is going down. If it's only simply supported, there will be an uplift force. Okay, so that's why normally we don't recommend using simply supported case. But wherever there is a simply supported case, you need to consider it as it is. Okay, there will be a change in terms of the bending moment value. When I say restrained, that there is some kind of fixity between them. So even if you put one screw, it does not give you the same fixity of boring the beams and the slabs together. If you are not having the same fixity, it means you are not having the same bending moments. And that will change according to the bending moment. I mean, the reinforcement will change according to the bending moment values. Okay, so now you see that this is my problem. They have given us the dead and live load. Okay, they have given us the dead and live load, and they have asked us to design the corner column here. Okay, they have asked us to design the corner column, corner slab, sorry, for the mild condition, and then they have given us a grade of 35 and a grade of 460 steel. So there are certain inputs which have been given already in the example itself. So the first thing, we'll go for a check for a one-way slab. Now, if we see our drawing, it is 4 as a short dimension, 5 as a long dimension. If we try to get your Ly over Lx, so Ly over Lx is 5 over 4. 5 over 4 is lesser than or equal to 2. It means that it's going to be a two-way slab. Are we clear with this point? Are we clear with this point?
Yes, sir.
Right. The next step is to check the support conditions. Now, going for the support conditions, we said it's a two-way slab, so it's either going to be simply supported or it's going to be restrained. Okay, it's going to be restrained. And once again, if you go to your construction site, you will see always that the beams and slabs are brought together when it comes to inside construction. Okay. When we are doing the construction in the site and we are doing the concreting inside the site, the slabs and beams are brought together. Okay. So it says for you it consists of restraint. So it's very clear that it's restrained. The general, once again, the general concept that slabs are restrained, unless it says for you in the question that this is a precast element or this is going to be a concrete slab resting on a steel beam. Okay, so the general perspective, in most of the cases, we are using only a restrained piece, unless it says for you. So if it didn't mention for you and it was a two-way slab, then directly you should be referring to it as a restrained slab. Are we clear? That's a general method of construction. Are we okay? Okay, so you can say it says for you restrained because the slabs and beams are brought together. So we're going to use the big table. We are not going to use a small table. So now we check that it's a two-way slab. We check that it's restrained. We need to check the material properties, whether they have been given in the question or they have not been given. So if we go to the material properties, we can see in the question clearly they have been saying that we are using a grade of 35 for concrete and a grade of 460 for steel. So these have been mentioned. If they have not been mentioned, you need to check your code to get the proper grade of concrete. And I'll explain for you later on how we are going to choose the grade of concrete and the grade of steel. So back, after checking the materials that have been already given in the question, we are going to go for durability conditions. Now it says for us, design the corner slab for mild condition using grade of 35 concrete and a grade of 460 reinforcement. So durability has been mentioned that we should design this particular slab to be a mild condition. Now we should understand what's the meaning of, what is the meaning of a mild condition. Let me, I want to try to get you the code. Okay, now if you see here, it has been defined by the code. Whether it's BS 5328. This is for specification of concrete, or BS 8110 as well. It has been mentioned. It says for you, if you are mild condition, it means that you are protecting your concrete from weather. Okay, so we are talking about the general weather. Okay, general weather where there is humidity, the condition is going to be mild. If the area that you are designing your building or your structure in is affected by rain, like for example Salala, where you are having seasonal rain, then you should be taking it to be moderate. So general environment, it's mild. If there is a rain, moderate. If your concrete is exposed a lot to the severe rain, then it's going to be severe. Here it is exposed but sheltered, it's like protected. Okay, protected from the rain, then we can have it as moderate. If a lot of parts of your structure is affected without protection from severe rain, then the condition considered is going to be severe. If your structure is affected occasionally, sometimes by seawater spray, you are living near to the seawater, then it's very severe. If we are designing something inside the water, frequently exposed, then you need to take it as more severe. Oppressive is wherever normally we design for heavy or critical structures, like structures where they are containing dangerous liquids, for example, or freezing situation. Okay, so according to these, we should know that our structure is available in this particular location. This particular location, whether it's affected by rain, whether it's affected by seawater, whether it's close to seawater or not, you can decide which condition to design for. Now, after deciding which condition to go for, you will be able to find in the second table, you will be able to decide which grade to go for. Now, the code says for you, if your condition is mild and you are having reinforced, then the proper grade is going to be C30. If you are designing your structure to be a moderate and then it was reinforced, then the proper is going to be C35. Of course, you can use more, but this is sufficient. Severe and reinforced is going to be 40, and it goes on. Are we clear? Are we clear how would you choose the grade of concrete if it's not given in the question? This will help you in your project. In your project, do not come later saying that we don't know how to pick the grade of concrete. Okay. Now, yes.
Mr. What about unreinforced, non-structural, and structural one?
And reinforced is wherever you are referring to BCC, for example. And BCC, according to the code, goes from 10 to a maximum of 15. Your BCC, you know the BCC, right? Your BCC does not have reinforcement. So the grade is normally around 10 to 15.
But what about the non-structural and structural? There is a PVCC for structural one? Right.
See, when you say there are situations where, for example, we are having elements which are taking very small loads. Okay, where elements are taking very small loads. In that scenario, you can consider it to be structural, but you don't require to have reinforcement because that is sufficient. Okay, so when we talk about structural element and non-structural element, structural element is mainly the element which is taking loads. Non-structural are elements which are normally not designed to take loads. Like BCC, BCC is not considered to be structural. It's not taking any loads. BCC is only made to protect my foundation from the soil, or to make sure that it's horizontal. Is it clear now?
Yes, thank you.
Now, when it comes to steel, we have talked about concrete. When it comes to steel, in the market generally, we used to have 3 grades. One is 250, that's mild. It has been stopped from a long time, so there is no mild steel now in the market. There are only 2 types in the market. One is 460, another one is 500. So 460, and then we have 500. Now, if we go and see the codes, for BS8110, you can see you can see one code says for you that you can go and use the grade of 460. And then the new version of VS Code, the new version of VS Code, the new version of the VS Code 8110, it says for you, you need to use it as 500. Now, if you go to the construction market right now, if you go to the construction market, you don't find 460. You find 500. And if you go to the new software, you'll see most of the new softwares are only considering 500 now. Okay, that's why when we opened TechNet, it was 500, but they changed it later to 460. Okay, nevertheless, whether you design your element for 500 or 460, you shouldn't have an issue. And I'll explain why. This is going to be the last point. Now, if you are using 500, okay, if you are using 500, there is a factor of safety for the material of steel. And the factor of safety for the material of steel, if we go here, okay, the factor of safety for the material of steel, if we go see, if we are saying the reinforcement factor of safety for the material of steel is 1.15. It means if I want to get the factored strength, 500 is my reinforcement strength divided by 1.15. So I'm considering only, even if it's 500 say to be the strength, I'm considering the strength to be 434. Anything more than 434, it's fine. I'm designing my element to be 434. That's if it's 500. Now, if it's 460, you can see the code now is changing the factor of safety from 1.15 to 1.05. So if we go once again to our calculator, now this is 434. If we go for 460 divided by 1.05, we are designing it for 438. And both values are very close to each other. That's why it does not really matter whether you are using in your actual design 460 or 500, as long as you are using 1.05 and 1.15. Now, where we are using 1.05 and where we are using 1.15, if you go and see 1 divided by 1.05, this will give you 0.95. And this is where we are using the equation of AS. If you remember, the AS equation is equal to M divided by 0.95 Fy and Z, Fy multiplied by Z. This is from where you have got the 0.95. 0.95 are coming from 1 divided by 1.05. So if we're using 460, it means that I'm going to use the equation of M divided by 0.95. If I'm using 500, then it's going to be 1 divided by 1.15, and it's going to be 0.87. So instead of using 0.95, we're going to have it as M divided by 0.87 Fy into Z. So that's why you will go, whenever you are doing or seeing other textbooks which are solving similar problems, you can see some of them are using 0.95, some of them are using 0.87. 0.95 for 460, 0.87 is for 500. Both of them are fine as long as you are using the correct thing. Doing that, we have finished today's lecture. Unfortunately, I wanted to continue the durability, but due to the explanation, we have taken a lot of time. But anyhow, we'll continue. We'll continue in the upcoming lecture. The only thing that you need to do right now is to go to your e-learning and try to solve your question. If you go to the e-learning, it should be active.